All right, so solving trig equations, and we're going to be solving these algebraically. We will use our calculators to check answers. So we're gonna go through. I've got 6 examples here that are kind of basic level examples. We're going to do all of them, and for each of them, we'll go through and give the solutions just on the interval from 0 to 2 pi. Do you guys understand what that means on the interval from 0 to 2 pi? It means that we're only going to give solutions that are between 0 and 2 pi. Okay, there are a lot more solutions out there, and we'll talk about that in a second, but we're only going to give our solutions between 0 and 2 pi. So this says that the sine of x, remember, if x is inside of a sine, it must be an angle. So x is going to be an angle where the sine value of that angle is equal to a half. So go ahead and look at your pink sheet. Somebody please remind me, when I'm looking for sine values, is that the x coordinate or the y coordinate of our points? That's our y coordinate of our points. So I'm looking for y coordinates of a half. Do you see some angles where that's happening? I see, and we always want to start at 0 because I like your answers in numerical order. So the first one I'm seeing is pi over 6. You see in pi over 6 also. The sine is a half here at pi over 6, so there's one of my solutions. And is there another one? Well, I told you there was another one. 5 pi over 6 also has a sine of 1/2. And I don't think there's any more. We've got a sine of negative a half here at 7 pi over 6 and negative a half at 11 pi over 6. But this is specifically positive 1/2. So those are the only two between 0 and 2 pi. So this would be our solution on that interval. That's it. That's it. Of course it'll get harder, but we're built up to it. It'll be fine. All right, so see if you can do the same thing for me for the rest of them. Now leave some room underneath each of these solutions because we are going to come back and give the general solution for this also. So we're going to be giving 2 forms of this solution. But see what you can do with 2, 3, and 4. And then I'm going to move it down here in a little bit, and I'll show you 5 and 6 also. So take a few minutes. If you guys could go ahead and copy down 2 and 3 and 4, so that I can move this down and show you 5 and actually I can just zoom out. Forget what I just said. Oh, out! That's the wrong way, machine. Come on. There we go. All right, I have some questions for you. My first question is, why did I not include 2 pi here, as well as 0 and pi? Why did I not include 2 pi? What do you think? Yep, so because of the instructions. The instruction said from 0 to 2 pi, including 0 if that's a solution, but don't include 2 pi if it is a solution. So that's just because of the instructions. Now, is 2 pi a solution to this equation? It is. So is 0 and so is pi. Can somebody give me another solution to this equation other than 0 and pi and 2 pi? Negative pi would be a solution. How do we know for sure that negative pi is a solution? Oh, because it's coterminal with pi, right? If we took pi and subtracted 2 pi, remember coterminal angles we can find by adding or subtracting a full circle, 2 pi. So if I took pi and I subtracted 2 pi, I would get negative pi. What if I added 2 pi? What would I get? I'd get 3 pi. Is 3 pi a solution to this? Yes, all of the coterminal angles of these are also solutions to this. So we're going to write a general solution to this. And let's start with the first one, actually. When we write a general solution, we need to give sort of a formula for how to find all of the correct solutions. Pi over 6 and 5 pi over 6 are two of the solutions, but they're an infinite number. I can start adding 2 pi on, or subtracting 2 pi from either one of these as many times as I want, and I'm going to get another solution. So I'm going to give my answer this way instead. I'm going to write it as pi over 6 plus any multiple of 2 pi. And I'm using 2 pi n to represent any multiple of 2 pi, and I'm going to specify that in this n is an integer. Do you guys remember seeing this whole n is an integer thing back in chapter 4? I told you it was going to come back, and here's where it comes back. And then that's not all, folks, because also 5 pi over 6 plus 2 pi n. And I've already got that n is an integer, so I'm not going to write it again. So the general solution is going to include your specific solutions between 0 and 2 pi, and also give information that I can add any multiple of 2 pi to that and get another solution. All right, so number 2. Let's write our general solution here. We got pi over 4 and 7 pi over 4. So pi over 4 plus any multiple of 2 pi, and 7 pi over 4 plus any multiple of 2 pi, where n is an integer. Yes, that's got to be in there someplace. Some textbooks will use k instead of n as their counting variable. K and n are the most common counting variables that they use in math. What's up? All right. So how do we go from a specific solution to the general solution? You just take each of your specific solutions and add 2 pi n to it. Except there are sometimes some better ways to write this. Now I will tell you, I'm not going to take off points if that's all you do. Okay, so if in number 3 you just said, I'm going to go ahead and say this is 0 plus 2 pi n and pi plus 2 pi n, where n is an integer, I'd say for me that's good enough. But there's a better answer than that. And if you're interested in finding the better answers, and you may have a professor later on that would say this is not good enough, and take off some points for this. It is technically correct. What helps me sometimes to find the other answers or to sketch where those points are on my unit circle. So I had 0 and pi. Is there some way that I can encompass both of those points? Like spinning around the circle? Here's my thought process. I could start at 0 and I could just add pi to get another solution, right? And then I could add another pi to get a third solution. And then I could add another pi to get a fourth solution, another pi to get a fifth solution. So my better general solution would be, I would just say this is pi n, where n is an integer. Yeah, and this question hasn't come up yet. Why don't I put a plus or minus here instead of just a plus? Because n can be negative. N is the integers, and the integers include negative numbers and 0 as well. So this would be the better solution. This is the simplest solution. This one works just fine. How about this one? Is that going to work here too? Can I just go pi n? No, we can't with this one. If I sketch this out, here's my unit circle on my x-axis. This one only includes pi, and then to get to my next solution, I'd have to go all the way around the circle and come back to it. So I'd have to do another plus 2 pi. So there is not a simpler solution to this. The simplest solution is pi plus 2 pi n. Let's see if this next one has a simpler solution than just listing them with a plus 2 pi n afterwards. So give me a rough sketch of your unit circle. Where is pi over 3 and 4 pi over 3? Pi over 3 is right here. That's at 45 degrees. And 4 pi over 3 is right across from it. Ooh, that's interesting. So I could just start at this pi over 3 and rotate around a half a circle. What did I just add there? Plus pi. And then if I kept rotating another half circle, I'd get back to that spot again, and then I could just keep doing plus pi, plus pi, plus pi, plus pi. So the simpler solution to this one would be pi over 3 plus pi n, where n is an integer. All right, I'll tell you from experience, some of my students like this puzzle of finding the simpler general solution, and some of them really, really hate this. If you don't like this and you don't want to do it, I'm okay with that. I will tell you right now on the test, if you write your answer as pi over 3 plus 2 pi n and 4 pi over 3 plus 2 pi n and stick a little sideways mustache out in front of it, and n equals, or n is a member of the integer set there, that's good enough. I'm okay with that. You're still going to get full credit. Okay? I kind of like I like the challenge of seeing if I can find a simpler way. I think there's a simpler way for this one too, isn't there? This I would definitely rather, because I don't want to have to write this plus 2 pi n out 4 separate times. That's silly. What kind of mathematician would want to do that? Okay, fair enough. Pi over 4 is here, 3 pi over 4 is here, 5 pi over 4 is here, 7 pi over 4 is here. Those are evenly spaced out. How far in between, what angle is in between each of these? What are we adding to get to the next one each time? We're adding pi over 2, yeah, 90 degrees or pi over 2. So the simplest way to write this would be pi over 4 plus pi over 2n, where n is an integer. But again, if you don't like that, feel free to write out the super long version with all 4 of those. Okay, that said, you may either write out kind of the version where you just have your specific solution, each with plus 2 pi n over them, or a simpler version of that. But please don't make my life more difficult by writing some crazy weird thing on the test that also happens to be correct, but it's going to take me like 5 minutes to figure out if it's correct. Okay? Please. Either simpler or the long way. Yes? Say that again. Oh, why did I do that here? Because there were kind of two things going on. Oh, why don't we close it? That's a good question. I don't know. Do you remember back in algebra when we were doing systems of equations? They always had this little thing out in front, and it was always just, no? You never saw that like that? Okay. Yeah, it's to let you know that it goes together. Yeah. That it's vertically going together, but they don't usually have one on the other side. I don't know. It's like writing it like this with the commas in between without the commas. Oh, that's a good way to say it, yeah. You could do it with 2 of them instead of. You could have them next to each other, and then you would close it on the other side. So if I put this comma this, then I would put that on the other side. But I'd have to put I suppose I could put this after. I think they would probably put that after the n bracket. Yeah. I don't know. Notation. It's a good question. You know, this is all this stuff is just arbitrary. Like whoever wrote the first book that caught on decided that's how they were going to publish it, and then everybody else did the same thing. Okay, you guys ready for some harder ones? Yes. Yes, you technically don't have to here. You might see it in some textbooks. They might do it like that. So they might open it and close it, or some of them, I don't think this would be a problem either if you open it and close it there. I'm not going to get picky about that kind of stuff, okay? I would like you to get in the habit, when you're writing your specific ones, I would like you to get in the habit, if there's more than one, of putting it inside of the set brackets. So I think the technical name for these is brackets. I call them sideways mustaches, but they mean it's a set. They mean the set consisting of these two numbers. And then technically, if you have a single element inside of a set, the brackets are not necessary. Okay, so yeah, let's not get too hung up on notation, as long as I can look and see that you know what you're doing. And again, if you're not a big fan of kind of finding these simpler ways of writing them, that's okay. That's okay. All right, I'm going to go way back to Algebra 1 right now and talk about something that's near and dear to my heart. I was actually just working with a student yesterday on some Algebra 2 stuff, and this came up. And I see this happen all the time in pre-calc, and I see it happen in calculus, and it's one of like the biggest common mistakes that people tend to make, like at every level of mathematics when they're solving equations. I'm actually going to do this problem two different ways. So I'm going to copy it down over here. So we're going to follow all the rules of algebra while we're solving this equation two different ways. We're not going to break any rules, but we're going to make some bad decisions in one of them. Okay. So I'm going to do it. I'm going to do this first. So I look at this and I'm like, I got x's on both sides of this. Boy, this problem would be a lot easier if I just divided both sides by x. And then I would only have x's on one side, right? We're allowed to do that, right? The division property of equality says that we can do that. Now, the division property of equality says that we can only do that if x is not equal to 0. Do we know if x is equal to 0? I don't know. But let's just say, okay, let's assume that we're safe. So what would that get us? That'd get us 2x equals 3. And then we could divide by 2 on both sides, and we got x equals 3 over 2. X is 1.5. Boom. And if you plug 1.5 into this original equation, you will find that it is a solution. Okay, so that's one way we could do this problem. What is the other potentially better way we could do this problem? All right, I got a little bit of a spoiler up here in my heading. Do you guys remember what the zero product property is? It's that thing that says if you've got a 0 on one side of your equation, then you can take all the factors on the other side, split them up, and make their own equations. In order to do this, we have to have a 0 on one side. So if I'm going to use the zero product property, I would first subtract 3x from both sides to get that equation. Now, there are no factors going on here. Well, there's a single factor going on here. But I could factor an x out of both of these terms. Now I've got two factors. And what am I allowed to do with those two factors since there's a 0 on the other side? We can set them both equal to 0 and solve those to get some solutions. And if I solve this, I'm going to get x equals 3 over 2 again. So this is, it's marginally incorrect. Well, all right, that's arguable. I see people trying to do this all the time. Why do we want to avoid ever dividing an equation on both sides by something including a variable? Because we don't know what it is, so we don't know whether it's equal to 0. Also, we lost the solution, right? We got the 3 halves both ways, but this way we got 0. Now, can you convince yourself that 0 is a solution to this equation? If you plug 0 in, it works, right? This method did not give us that solution. So we always want to avoid dividing both sides by something that includes a variable, because when you do that, you tend to lose solutions. All right, so the reason I went over this is because I see people doing this so much on our test for a problem like this. So go ahead and write this down. So we're getting a little bit more complicated here. It's not just a trig function of an angle equal to some number. We can't just look at our sheet to find a solution to this. We're going to have to do a little bit of algebra first. I had a problem similar to this on our test last year, and I had so many people say, you know what, I'm just going to divide on both sides by sine x. Then I'll have 1 equal cosine x, and that'll be easy. I'll write down those solutions and we'll be done. That's problematic, though, because you're going to lose some solutions if you do that. So let's instead get a 0 on one side. Would y'all prefer to have the 0 over here or over here? On the right? 0 over here? 0 over here. Okay. 0 equals sine x cosine x minus sine x. I'm not showing my steps, but maybe I should since it's our notes. And then, does that factor? If we were thinking about dividing by sine x at the beginning, then that means we should probably be able to factor a sine x out at this point. And it does. We can factor a sine x out, and we're left with cosine x minus 1. And now we can split it up and make two equations. Sine x equals 0, and cosine x minus 1 equals 0. And then this is all ready for our sheet. We'll come back to it in a minute. I would like to just have this cosine by itself. Let's do plus 1 on both sides to get cosine x equals 1. So from here, we're going to our unit circle. Let's just give the solutions between 0 and 2 pi, first of all. So I need to list out all of the angles where either sine is equal to 0 or cosine is equal to 1. I need to find all of them. So looking through, sine is equal to 0 at 0. Right, so 0 is going to be one of our solutions. So at 0, where else is sine equal to 0? At 180 or at pi. So that happens at 0 and pi. And cosine x is equal to 1. Where does that happen? Cosine x is equal to 1 at 0. Oh, that's a repeat. Huh. Yeah, it was here and it ended up here as well. Interesting. Cosine x is equal to 1 at 0. And that's the only place, isn't it? So if I combine these together into a single set without repeating anything and go from least to greatest, my overall solution is 0. 0 and pi. On the interval. That's it? Of course not. See if you can give me a general solution to that. And I challenge you, if you are interested, to try and go straight to a simplified general solution. For me, it really helps me to visualize the unit circle and to draw all of my solutions from here. 0 is a solution, pi is a solution. Oh, I can hit those in a single rotation. Yeah, and then I'll just keep, so I could do 0 plus pi n, or I could just do pi n, right? That'd probably be the simplest way to write the general solution. But if you prefer, you could write 0 plus 2 pi n and pi plus 2 pi n and n is an integer. That's fine too. That's fine too. Any questions on that one? So what's my big message to you when you see an equation that's got a sine x or a cosine x on both sides? Are we ever going to divide to get rid of that thing? No, we'll get a 0 on one side and factor it out. If you're ever tempted to solve an equation by dividing by something that has a variable in it, get that 0 and factor it out instead. All right, we got 2 more. Oh, this looks like fun. Look at that one. Nice. Ooh, I like you're seeing that. I just heard quadratic. Are you seeing a quadratic equation here? So in Algebra 2, you spend a lot of time dealing with quadratics, and then in pre-calc, we start looking at equations that are quadratics, but they're really fancy quadratics. But a quadratic is just something that has a squared term and a term that's not squared, and it could potentially have a constant term as well. I'd say this is a quadratic equation. Now, some people don't like solving quadratic equations that have all that fancy stuff in it, but we've got a nice psychological tool for this. Do you remember W? Let W equal, what's the fancy thing we'd like to get rid of in this equation? Cosine x. So let's let W equal cosine x, and then we don't have to deal with all that kind of messy stuff. If we let W equals cosine x, this is just 2W squared equal to 1 minus W, and we should feel pretty confident solving an equation like that. How do we solve quadratics? We've got a couple different options, 3 different options I can think of. Completing the square, which I don't like doing that much. I don't know why. I just got a block against it. Quadratic formula in which you got to have a 0 on one side, or factoring, which you got to have a 0 on one side. Let's get a 0 on one side and see if we can factor it. I think I'm going to do minus 1 and plus W on both sides, so I keep that 2 positive. And then from here, it depends how we want to tackle this. If you're an Xbox enthusiast, you'll get after that right now. This problem is way easier to just guess and check. Right? There's only one way I can think of to get 2W squared. 2W and W. And there's only one way I can think of to get 1. 1 and 1. And then all I got to do is, I know that one of these ones is going to be positive and one's going to be negative if they got to multiply to give this. So I just got to figure out which one's positive and which one's negative. And I think I can make it work if I do this positive and this negative. However you want to do it. If you did the whole, it does matter. Yeah, this has got to be, the minus has to go with the 2W. If you're an Xbox person, you would have done this instead. You would have said A times C is -2 and B is 1. And what are 2 numbers that multiply to give me -2 and add up to 1? That'd be 2 and -1. And then you go draw the box, and you'd have 2W squared here and -1 here. And the 2W and the -1W here. And then you'd say, this is 2W, and this is W minus 1. And plus 1, and you would get to the same answer. And that works. It just takes forever. All right, and then what do we do next? Yeah, we set them each equal to 0 and solve. Now, we've already dealt with polynomial equations, so I'm okay. Hey guys, don't miss this. I'm okay with you going straight to W equals 1/2 and W equals -1 if you're comfortable with that. If you want to show the steps in between, you can do that too. If I did want to show the steps in between here, I would write 2W minus 1 equals 0. Add 1 on both sides to get 2W equals 1. Divide by 2 on both sides to get W equals 1/2. But if you can kind of envision those steps and jump straight to here, that's fine. You can leave all of this out. You decide, okay? You decide what's going to be best for you. Are we okay with W equals 1/2 and W equals -1? Are we finished? No, because W is holding the place of cosine x. So let's substitute cosine x back in. Cosine x is a half. And cosine x equals -1. And then we'll just figure out all of the angles where that happens. So let's see. That happens at 60. That's pi over 3. It happens at 300. That's 5 pi over 3. And where's cosine -1? It's at 180. It's pi. I'm practicing with my memorization, so hopefully I don't miss one next time. But if you don't have these memorized, then remember you've got your wheel of fun where you can find them. So cosine is a half here at 60, or pi over 3, and also at 5 pi over 3, and cosine is equal to -1 at pi. So we do want to put these in numerical order when we write our general or our specific solution. So our solution on the interval 0 to 2 pi would look like this. Which one comes first? Pi over 3 is the smallest, right? And then pi, and then 5 pi over 3. General solution enjoyers, see if you can write me a nice, simple general solution for this one. This one's kind of interesting. Nice. It's easier for me if I can visualize where those are. So one of them happens here at 60. One happens at 180, and one happens at 300. And that's convenient because how far apart are those things? They're all 120 degrees apart. So the simplest way I can think of to write this would be pi over 3 plus 2 pi over 3n. N is an integer. Actually, maybe pi plus 2 pi n all over 3. That looks simpler yet. Nah, I like the first one better. Okay. Ready for one more? Any questions on this one before we get out to our last one here? All right, here we go. Sine of 2x equals cosine x. So, ooh, I love that. I'm hearing people talk about identities. We did practice with these identities on Monday. It was actually part of the same section, and there's a reason for that. Now, this is possible to do without an identity, but let's do it with the identity first. Do you guys have sine 2x memorized? It's probably the most used of the 2x ones. It's 2 sine x cosine x equals cosine x. Oh, I know what we could do next. Let's divide on both sides by cosine, right? Right? No. What should I do instead of dividing by something with an x? Get a 0 and factor it instead. All right, you guys got this. Go ahead. Get a 0 over here. That'll be your first step. And then see if you can factor something out. And then split that up into 2 separate equations and solve. I feel like you guys got this. I'm going to work it up here just in case you need a hint. Feel free to check up here. But try and do as much of this one on your own as you can. Oops. That's not my GCF. Well, we could simplify it a little bit. We don't need to have 4 things. It should be over 6. If you're seeing any mistakes here, shout them out. They're all wrong? Oh, man. We could simplify this, I think. Pi over 2, 3 pi over 2. So those two we can simplify. Pi over 6 and 5 pi over 6. Ooh, how about this? Pi over 2 plus 2 pi n. And pi over 6 plus 2 pi over 3n. That's wacky. Because these 3 are all 120 degrees apart, right? Yo. I've not seen it done that way. No. Let's keep the plus 2 pi n with the thing. Yeah, is it? You're asking, could I? I don't know. I've never seen anything like that before. But do some research. Show me that it's out there someplace. And so, like, I'm trying to think of an example. So, like, here's a set: 5, 6, 10, 11, 15, 16. Do you see my pattern? ... So they're in pairs, right? And they're consecutive pairs. So would that be, could I call that 5 and 6 plus 5n? That looks weird to me. I don't know. Do some research. If you want to try and use a different notation than this, then find me an established textbook or paper or something where they're using that notation. Sure. All right. What questions do you guys have? Focus on the 0 to 2 pi. That's how I'm going to have it. That's how it's going to be on your test. But I encourage you to try and find a simpler way to write things too. That's what I got. Let me show you the assignment. It's relatively short.